All right, let's start finally with Math 30-1, because if you think about it, we did all this wonderful review so far, but we haven't really gotten to the meat and potatoes of Math 30-1. Remember the name of this unit? Transformations and functions. So we're looking at transformations. Well, surprisingly enough, we've done it already, especially when you look at Math 20 in terms of all those parabolas that we talked about. Remember how we moved a parabola that was normally here? We moved it to, let's say, over here, or we flipped it upside down and moved it, or we made it wider or narrower or whatever it was. Those are all called transformations. But the whole point of Math 30-1 then, ladies and gentlemen, is that we're going to do this to all the functions out there. Every function that's out there can follow a specific pattern of transformations. Well, wait a second. The graph is going to change, and the big thing that you have to remember, as soon as you change the graph, guess what? That results in an alteration of the equation. Aha, I see. So, here's a little note for you. Right here. What are the things that we're going to look at? The first thing that we're going to look at is a location change. So we're just going to slide it to the right, or slide it to the left, or slide it vertically, or slide it down. Whatever we do, whenever we slide something, we call that a translation. So in other words, a translation, not a transformation, it's a type of transformation, but specifically a translation means that we're going to move it horizontal or vertically. That's it, okay? Now, the other thing, remember the stretches that we did, making it wide or narrow? This is going to change the shape of our graph. We're going to call that a stretch. So they're called vertical stretches. That's what we did in Math 20-1, where we made it narrow or wide. But now in Math 30-1, we're also going to do something called horizontal stretches as well, which is going to open up a whole new can of worms for us. But the thing is, it always follows the same pattern. I'll show you what we mean as we're going through this. The next thing, orientation. Those are also things that you did in Math 20-1. But in Math 20-1, we went across the x-axis, where we had something like this suddenly become something like that. Happy, sad parabolas, remember? Okay? But now in Math 30-1, we're going to take something that's over here, reflect it across the y-axis now, and make it over here. That's the 30-1. So if you think about it, there's only two extra things that you're going to learn here in Math 30-1. But the cool thing is, you're going to learn how to do this for all equations out there. Whether it's a linear, whether it's a quadratic, whether it's an exponential function, who cares? You're going to be doing it for all of them. And I'm going to show you how to do that. That's the exciting part. Okay, so enough of me talking about it. Let's get to it. Now, here's a couple things we got to know. After transformation, the point on the original graph corresponds to the points of a transformed graph, or what we call the image graph. You're going to see that in questions, especially diploma questions. They like using wording like image graph and so on. So in other words, basically what we're going to look at is we're going to take something from over here, and let's say here's our graph, there's a point there, and we're going to somehow transform it so the graph looks like this and the point becomes over here. How did we get from here to here? This being the original graph, this being the new image. Got it? Okay. Now, we're also going to use something called a mapping notation, which is going to be really cool. An example of mapping notation is going to look like this. It's going to say, okay, you've got an X, how did you move it? You got a Y, how did you move it? In this case, look at this. If we've got a Y and we did this to this, this implies that the original point has been somehow translated to that. And what this basically means is if the value of k is, let's say, 2, what you do is you leave every x value alone. Now, y, subtract 2. Every y value, you subtract a 2. That's what a mapping is all about. So, similarly, look at this one. This one says an xy. We're going to change it to an x minus h. Implies, again, that this point has been somehow translated to this. So again, Let's let h equal to, I don't know, -3. All right, we'll make it -3. Great. So if you look, this is x minus a -3, which means x plus 3. And guess what? That means we're going to be moving the x values all over the place. And the x values are going to increase by 3. That's how this works. It's nothing really overly difficult, and a lot of this you've seen already. Case in point, let's look at this. Finally into lesson 1. So all of that was prequel to this. All right, so let's check it out. First things first, it says a translation is a type of transformation. So translation, transformation, those tend to be a little bit strange, okay? Now, translation, just think about it. If you move from country to country, you have to translate the words, right? There's translation. Translation means a move or a slide. Okay, so you're going to move or slide an object from its original position to a new position through, oh gosh, this is just erasing everything, through a specified distance. You can move it vertically, or you can move it horizontally, or even both. Okay, so let's go to the first types of translations, called vertical translations. Vertical translations, you kind of did this already last year. You know all about this, but remember, you had something that looked like this last year. Specifically, you had an equation that said y equals ax minus p squared plus q. Remember, watch your p's and q's. Your p and q ended up being the vertex. Remember this? Yes, it's like a nightmare, but it's coming back to bite you. Whew. Okay, now, if you look at this particular notation then, you have to remember the q stood for the y-coordinate of the vertex. So you're dealing with y's here. So if you're dealing with y's, you're dealing with a motion up or down, right? So the Math 20-1 notation was this, okay? You had some sort of original function plus a k, which means a vertical movement of k units either up or down. Right? Math 30, we like things a little bit different. Notice in this here, we actually moved the k from here to the other side. Why would we do that? Why would we go, okay, originally this was y equals the function plus k. Now I'm going to take this, I'm going to subtract k for both sides here. I'm going to have y minus k equals to af of x. Why did we move this here? Oh, by the way, why did we change it from Q to K? I don't know. They just changed it for some crazy reason. So now we're not dealing with Q's anymore. We're dealing with K's. Well, okay to that. Okay. Now, what's interesting is why did we move it over to the other side? The reason why we moved this thing over to the other side is very important. Because if we keep these guys together, this strongly suggests that we're doing something in the y value. So we're keeping this separate. We're keeping all the y movements or translations or transformations or stretches or whatever you want to call them, we're keeping it on the y side. Here, we're keeping this on the x side. Why? Because this strongly suggests that we're doing something with the x's. Got it? Super simple. Watch what happens. Let's use this new Math 30-1 notation on this particular graph. You may recall something like this from Math 20-1. Absolutely you do. Okay, so look, here's our first graph. Y equals to x squared. As a matter of fact, I've actually graphed it for you. Yeah, I went into my calculator, hit y equals to x squared, hit the graph there, and I got this beautiful little graph looking quite like that. Oh, how pretty. Okay, so with that in mind, check this out now. Let's go back to our original. So there's my y equals to x squared, and you can quickly do this and say, okay, it's at the origin. The first one is 1, 1, 1, negative 1, 1, 2, 4, up here, negative 2, 4, and we drew a beautiful line coming down like this and around, and it looked an awful lot like that, right? Do you remember that? Okay, now let's go and do this one. Now, if you think about this, using Math 20 notation, Okay, you'd bring the 3 over to the other side and realize that this is x squared plus 3. So what was the p-value? What was the vertex value here? Well, the vertex value was 0, and this would be 3. So all you're doing is you're shifting this 3 units up. Do you remember? There's 3. So what does that mean? That means this dot here was also shifted 3 units up. 1, 2, 3. There's the new dot. This dot here was also shifted 3 units up. 1, 2, 3. There's the new dot. This one, 1, 2, 3 up here. And this one, 1, 2, 3 up here. So you're going to get a graph that looks an awful lot like that. So it's exactly the same graph, and all we did here is we shifted it. That's all we did. Take a look at this one over here. Same nonsense. Exactly the same nonsense. Here we go. We're going to take this plus 3, going to just bring it over back to the other side. We got y equals to x squared minus 3. So this means that we're going to shift everything from my original graph down 3. So this goes down 1, 2, 3, which means this point here is down 1, 2, 3. This point here is down 1, 2, 3 to here. Okay, this point here is down 1, 2, 3. This point here is down 1, 2, 3. So you're going to get a graph that looks like that. And again, if you look at this particular graph, we have not changed the graph at all. It's not wider, it's not narrower, it's just moved. And that's the whole point behind this statement. It says, what is the effect on the parameter k on the graph of this function? If you look at k. Don't look at the negative. Just look at k. K is a movement up or down. Okay? All right. Now, let's fill in the blanks. All right. So, compared to the graph of normal, when we put a minus k in there, or we do what we did in Math 20, leave it as positive k, this results in a vertical shift of k units. And if k is greater than 0, we move up. And if k is less than 0, we move down. But I know what you're saying. Well, what about that negative? What about that negative? Look, watch what happens. If k is positive, you pop it into this, you in fact get y minus k equals to f of x. But if k is negative k, watch what happens. You put it in here, you get y minus a minus k, which becomes y plus k equals f of x. You just have to remember that k was, in fact, not positive, but negative. So look at this. Last little thing, and I'll let you go. It says the notation y minus k equals to f of x is preferred over this. Why? Because the emphasis is placed on the transformation of y. So you leave the emphasis with the y's because you are, in fact, going up and down.